In this video, we're going to discuss a second example in which we will sketch the curve. So the curve in question will be fx is equal to x plus 4 over x. Okay, and we can plot an xy plane here. Okay, I'm going to label the axes. X and y, so we'll just do a few ticks here. 2, 3, 1, 2, 3, 4. 1, 2, 3, 4. Okay. So now let's, as you see here, 4 is divided by x. So obviously there will be an asymptote for at the line y is equal at the line x is equal to 0, which is the y-axis, right? So let's take the limit to see the end behavior as x approaches infinity of this function. So we would have infinity plus 4 over infinity, which gives you infinity plus 0, that's infinity, right? So as x approaches infinity, the function approaches infinity as well, right? And the same thing to see the end behavior as x approaches negative infinity of the same function is going to be that minus infinity plus 4 divided by minus infinity, that's minus infinity plus 0 equals minus infinity, right? So x will fall, the function will fall as x decreases infinitely, okay? So now let's try to find the so as we said, the x is equal to 0, that's the y-axis, right? And that's an asymptote. So that means if we try to if we try to put x is equal to 0, we will get an undefined value for the function, right? How about finding the x-intercepts? That's when y is equal to 0, right? The fx. Okay, so x plus 4 over x. And we're trying to find the points when this graph hits the x-axis, right? That's precisely what the x-intercepts are. So multiplying both sides by x, we will get 0 is equal to x squared plus 4. So that means negative 4 is equal to x squared. And what does that tell you? It's not going to be a real solution, right? Because you cannot have a negative 4 in the square root if you take the square root to solve for x, right? So it means that there are no x-intercepts. So the graph will not touch the x-axis anywhere, okay? So now let's see the end behavior of this function as x approaches the 0, the precisely the asymptotic line from the right. Okay, x plus 4 over x. So as we know, from the right means that the values of x will be positive, but as the x values get closer and closer to 0, this guy 4 over x will be infinitely huge, right? So as a result, it will be infinity, and this small x will not matter. And the same thing as x approaches 0 from the left, dividing by this infinitely small x here will make 4 over x infinitely small, right? So as a result, we will have negative infinity. Okay, now let's take the first derivative and see what's going on there. So we will have 1, right? We're going to differentiate the given function here just once to get the first derivative. So we'll have 1 minus 4 over x squared. Okay, now if we set it to 0, we will find the critical values, right? Is equal to 0, multiplying both sides of the equation by x squared, we will get x squared is equal to 4. Okay, so x will be plus minus 2. So there are critical points, critical values are x plus minus 2. So let's, so the first derivative is equal to 0 there, all right? So, and we're not sure whether or not it's an inflection point, but let's find the value of the function first at these 2 points. So when x is equal to 2, we get 2 plus 2, so that's 4, right? 2 comma 4 is the point. That's the critical value of the function there. And then when x is equal to negative 2, we get negative 2 minus 2, right? Because 4 over negative 2 is negative 2. So negative 2 minus 2 is negative 4. Okay, so negative 2, negative 4. That's another point where the slope, the instantaneous slope of the curve is 0, or where the first derivative is 0, right? So now let's use the number line really quick for the first derivative and see what's going on different sides of those values that we found. Okay, so we know that at 0 the first derivative is undefined, right? Because this is the first derivative equation, right? If you plug in 0, you will get an undefined answer, right? So at 0, we can mark it as an x bracketed, that it's going to be undefined. At x is equal to 2, we just found out that the value was 0 of the first derivative, and the same thing for negative 2. It was 0. Now to the right of 2, let's see, to the right of 2, if we plug in 3, we will get 1 minus 4 over 9. It will be positive, right? And as x increases, it will get more and more positive, so the first derivative will be positive. Between 0 and 2, let's try 1. It will be 1 minus 4. It will be negative, right? Negative first derivative. And for the between negative 2 and 0, it will be the same thing. It will be negative. If you test negative 1, since it's in the x squared, it will be squared. It will give you the same answer as 1. And to the left of negative 2, it's going to be the same, because obviously there's a symmetry involved here, right? Because of the x squared in there. So it will be negative here, I think. No, wait. Symmetry, yeah, it's going to be positive, right? You can test out the x values, but it will be the same thing because of the x squared, right? So there's symmetry involved. So now you see what's going on with the first derivative around those critical values, critical points that we found. So basically what this means is, so 0 as at this point, the first derivative is 0 at x is equal to negative 2, right? To the left of that is a plus sign, so it means that the slope will be positive, right? So it will fall from the right to left, right? Because it's positive, right? Positive means it's going to increase, the function will increase from left to right. And between negative 2 and 0, it's going to be negative. And that makes sense, notice, with the fact that we found that as x approaches 0 from the left, where was that? That was here. We're approaching negative infinity for the function. So that makes sense that the function infinitely falls as x gets closer and closer to 0 from the left. Now, between 0 and 2, we have a negative first derivative, so it means the function decreases as well, right? And that makes sense because decreases means from left to right, right? So it increases from right to left. We can think of it this way, right? So it rises to positive infinity. And notice how it makes sense with our assumption, well, our deduction before, because we said that as x approaches 0 from the right, the function approaches infinity. And that's exactly what's going on here, right? The function seems to rise infinitely, okay? And of course, to the right of this critical value of positive 2, the first derivative is positive, right? So the function starts to increase, and it just keeps increasing and increasing and increases, okay? And of course, notice that these graphs will be symmetric with respect to the origin, right? There will be an origin symmetry here. Now let's understand what the second derivative is, just in case. Let's test out the second derivative just for fun. So we're gonna have f double prime of x. We're gonna differentiate this function, the first derivative function we found. So 1 will turn to 0, and then we can write the first derivative as this: 1 minus 4 x to the negative 2 so that you can use the power rule conveniently, right? So it will be 0. I'm not going to write the 0. Well, I can write the 0 just for fun. And then plus 8, right? Because negative 2 times negative 4 is 8. X to the negative 3. So it means that it's going to be 8 over x to the third. If you try to set the second derivative to 0, you will notice that there is no way that you will get a 0 unless it's infinity or negative infinity for the x. And that makes sense because there are no inflection points, right? This first derivative critical point there, it's not an inflection point, right? Because as you can see, this resembles concave down, this curve, part of the curve here, and this in the first quadrant, this part of the curve represents concave up. And let's test that. Let's test the second derivative on the number line to make sure that it's actually correct what we're talking about. So we know that it's undefined at 0, right? Because you cannot plug in x is equal to 0 here, right? So at here we can just mark it with x and put it inside the square there. And if you plug in positive x values, you will get positive second derivative. And if you plug in negative values, you will get negative second derivative, right? And negative second derivative means that you will have concave down, and the positive means concave up. And that's exactly what's confirmed on our drawing of the graph here, right? It's concave up for the positive x values, right? Greater than 0 for the x values. And for the x values less than 0, it's concave down, and that's precisely what the figure looks like here. So this is pretty much it. I hope you enjoyed this tutorial. Please subscribe to my channel, and I'll see you in my next video.